we will go ahead with that whatever the portion we want to study. Okay, so whatever the portion missed, okay, I'll take tomorrow one class, and you spare me another one more class on day after tomorrow. Maybe if you are going to give morning also, it's better, because day after tomorrow I have some other work. So give me one more Friday. Can you give?
Yes, sir. Sir, 12 to 12:50.
Sorry, is it possible morning session? Early morning?
Sir, morning we have CIR, sir, actually.
Even 8 to 9?
We have technical programming, sir.
Sorry?
We have technical
Yes, sir,
programming.
okay, 8 to 9 it is fine.
Technical.
Sir, 8 to 9 I'll ask others. They're okay with the fine.
Okay, you check with them and you update me the timing, because Friday most probably I have, okay, if you are going to fix it something 12 something, it's going to be a really tough for me. If you can fix morning 8 to 9, so just I'll take a 50 minutes class and I'll wind it up. Because I don't want to, tomorrow I don't want to take a 2 hours class and all.
Yes.
I need to discuss two concepts. One is uncertainty, and uncertainty analysis I need to take, and some more things, something, and also how to calculate a blowdown time for a supersonic tunnel. These two things I need to discuss. So maybe I'll discuss the concept. I'll discuss the problems also, because that is essential for you in future. Okay, sir. So now I'll discuss. Okay, I'll give a recap of that. Sorry, whatever the portion you are going to prepare. Okay, for your exams and all. Then I'll come back to that your radix Pittard formula. Okay. Present. So if I can finish, okay. If I can finish. If I can finish my class tomorrow itself, I won't ask for any other class on Friday. Okay. Okay, sir. We'll go ahead. Okay. Now you need to look at that. Okay. Your first part is your velocity measurement. And your pressure measurement. Okay. Mainly you have to know your Pittard static view. Even last class also, previous classes, okay. What are the things we can measure with the Pittard static view? Okay. Dynamic pressure, how, okay. Your correction for compressibility. Please note it down. It's going to be useful for your preparation. And in the Pittard static view, okay, your design features. That is, okay, you have a length of your vertical stem, and length of your horizontal stem. Why there is such a kind of, why you have to choose a length like that, and also your location of static pressure post. Okay, so why you are choosing that static pressure post like that, and what are the shapes of core body for the shapes of core body target. So I think if you have any issue in each and everything, okay, maybe a class is, you can put up a question in the WhatsApp group. I'll provide consolidated all of your questions, okay. I'll discuss with you. It's not an issue. It's not a problem. Even anytime, okay, from 7th to okay 13th, whatever the questions you there, you can give a call to me. If I am free, I'll answer to your call. Or otherwise, okay, you put your question. I can call you back. It's not a problem. So look at that. Okay, these things. And in the case of your supersonic condition, your measurement strategy for static and stagnation pressure. I think already I discussed about the static pressure measurement. Okay, you have a semi-wedge configuration like that. Okay, and we are going to have a port is going to be here. From these we are going to measure your static. This one. So what will happen here? Your oblique shock is going to form. This is the oblique shock. Okay. So here no shock formation. You can measure your static pressure. Same way your stagnation pressure measurement, you can take it as your Rayleigh Pindal formula. Already we have discussed, okay, but I'll discuss once again. Rayleigh's Pindal. Okay. So anything if it is anything more than that, okay, like your calibration, determination of Mach number. Determination of Mach number in the supersonic tunnel dissection. Okay, so this is another one more. Okay, already we have talked about that. Okay, if it is a Mach number is going to be less than 1.6, 1.622, these three genes. Okay, we have discussed four methods, possible 4-5 methods. Okay, just to go through that. Still, if you have issues, you can come back to me. I'm ready to clarify your doubt once again. Because these are all essential for understanding the outcome of your EAD, experimental aerodynamics. For understanding the outcome of your experimental aerodynamics course. Okay, and anything else? This is your based on your this one. And next one is okay. Your temperature measurement. You need to know, okay, your operating principle. Okay, what are the various ways, various methods. Okay, various methods, and if it is a thermocouple principle. I talked about total probe and static probe. Total probe for temperature measurement. Okay, so this is the one you need to know. And also in terms of your hot fire anemometer, just look at that constant temperature alone. Constant temperature. That's just a principle. Constant temperature anemometer. Okay. So yeah, Wheatstone bridge, how your principles and all, how are we going to get the data and all? Just look at that. That's all. In addition to that, mainly you need to know flow angularity. And your turbulence measurement. compressor sphere, okay, turbulent sphere and all, and hardware and market. Okay, those things are coupled. So that's all in these your intrusive type measurements and all. And also, other than that, you need to know, okay, types of your wind tunnel, both subsonic and supersonic. And what are those design features? Means components and its functions. I think it's all very easily you can understand. Okay, you can look at that. If you have questions, so please discuss it in the group. So we will find out answer for that. Even okay, your friends also means students also can, okay, if you have a correct answer, okay, you can post it on that. If your answer is correct, okay, I won't say anything. If it is something wrong, then I will correct you and we will go ahead with that. It's not an issue. Okay. So types of internal and also mainly you need to know your blowdown tunnel. Blowdown tunnel in the case of a supersonic. And simple open circuit tunnel or subsonic. So mainly for these two tunnels, you need to know your components and its functions. And non-intrusive measurement. Okay. Look at your Schlieren, your Shadograph. Okay. And also your PAVs and LTV and your brief. Okay. Okay. This alone you look at that. You don't want to look at anything more on that. Okay. And also your pressure sensitive plates. Your pressure sensitive plates. But while looking at that, please look at that in detail. Try to understand complete theory. What is your this one and all your advantages, disadvantages, operating principle. Okay, so those things you need to know. Anything more? Yeah. Other than that, mainly you need to know your flow visualization. Okay. One is your smoke flow visualization. Tough. Okay. And yeah, surface flow visualization. And your water flow channel. So these are the things, okay, if you are going to study these things, that is sufficient enough. I think you can perform well in your examinations, okay. No issue on that, okay. You can go ahead. Any questions, sir? Anything else? Any question? Any questions? Sir, please discuss. Please say something. Yes or no. because sitting in front of a monitor and I'm speaking, but no response from your side. Please speak something.
No, sir, no question.
Yeah, it's good.
Got
Thank you.
it, sir.
So, if you felt that okay, if I'm going to have anything, okay, you can put a message to me, something, okay, if you felt difficult in understanding some things that you need a clarity, please tell me, I'm ready to clarify that. And still, any issues, okay. In addition to that, okay, I'm going to take up two things, okay. Already I mentioned about Rayleigh-Bennet formula. Rayleigh-Bennet formula. And the next one is your blowdown time for supersonic control. Okay. And third one is, okay, I need to talk about that, okay, your uncertainty estimate. And the other thing that normally we used to do, for example, with the help of a probe, okay, if you are going to have an unsteady response, okay, for example, okay, you are going to have a time response and an unsteady response, okay, if you are going to get informations like that, from there, this one, how are you going to separate the frequency, do a FFT analysis? Already you fast Fourier transforms and all you might have studied in your mathematics, okay. Okay, you need to know how to separate this one as a like a your average data and what is the your instantaneous variation and all. And also, if you do your FFT analysis, you'll be getting a what is the dominant frequency, what is the your power spectral density, those things and all. You need to know, because from that only particular pressure signal or temperature signal you are going to calibrate the data. So just these things are going to be out of your mathematics, okay. Just to look at that, okay, you search for a FFT, those things, fast Fourier transforms. Okay, so I'm going to take up these three things in the remaining classes until whatever the classes I'm going to get. From that I'm going to do that. So you need to know your Rayleigh-Bennet formula. Rayleigh-Bennet formula. Okay. In the Rayleigh-Bennet formula, if I am going to keep a Bennet static cube in the your flow, okay. So what will happen if the Mach number is going to be supersonic, okay, greater than 1? If your whatever the your theta here, if it is going to be greater than theta max for the particular Mach number, what will happen? Your sock is going to be detached from the surface. You know about that, this one. Okay. So if you look at that, the detached sock, okay, the central VGB is going to be normal to the flow, and afterwards it's going to be turning like that. So what we used to do is we are going to assume this one as a normal sock. Okay. So you can ask, okay, if you do a course on hypersonic flow, okay, there we'll be taking it as a subsonic region. Okay, where your Mach number is going to be less than 1. Okay, so here the Mach is going to be greater than 1. Here also Mach is greater than 1. Okay, because the flow is going to be, these regions are going to be, while do your detached sock analysis and all, we used to do like that. So there will be a slipstream will be there, because across the sock, okay, your strength is more, P2 by P1 increase more. But if you look at that, your P2 by P1 is going to be less. Okay, so automatically there is a difference in your pressure gradient. There is a slipstream will form. Slipstream means at that point your pressure is going to be same. Okay, so we are going to have a detached sock. Okay, we are going to treat that as a normal sock. Okay, if we take 1, this as a 2. Okay, we can the P02 by P01. Okay, we can write as a function of your Mach numbers. Already we have the relations with us. Okay, so if you refer your stagnation pressure rise, stagnation pressure drop, stagnation as a ratio across the sock, across your normal sock. Okay, so automatically what we can do, okay, using that we can write that as a function of Mach number, and also your pitot tube is going to capture your P naught. Your pitot tube is going to capture your P naught too, and from the wall static pressure we can get the P1 value. So using these, okay, if you do a chain rule, okay, you can get your this one, your so your stagnation process jump across your this one. See, that relation is going to be little bit of complicated one. Okay. So they are going to give P naught 1 by so we can determine the Mach number. See here, I took it from the MIT OpenCourseware website. Okay, so this is your P02. Okay, so with the help of whatever your this one. Okay, so this is your pitot tube, pitot head. Okay, your detached. Okay, this is going to be 1. This is going to be 2. So your pitot tube is going to capture your P02, and also I can get the P1 value, and okay, from your wall static pressure, okay, particular location I can find out a wall static pressure, that I am going to assume it as a P1 here. Okay, so now P02 by P1 I am going to get as a function of your M1, that is your Mach number. So you can resolve it, and you can solve this equation pitot formula, and you can get the P02 by P1 value. Look at that. Okay, now this is your P01 by P1. Okay, this is a relation. So if you consider that you are isentropic, what is the deviations and all, you can see very easy. So that is the case. Okay, first one P02 by P1 is going to be based on the whatever the presence of sock we are going to assume it as. But if we assume that there is no sock, okay, automatically what will happen? P01 is equal to P02. Okay, we can use simple relation, this your isentropic relation itself. If you look at that, the deviation, you can see that. Okay, where the error. See here. Beyond your Mach number 1.4 itself, okay, you can see that. That is it. Your ratio is going to deviate. So you can use if your tunnel and all, it's going to have a Mach number of 2. Surely you have to use your Pitot formula for estimating the Mach number. Okay. Any questions, sir? If you want, I can share that chain rule, how we are getting it and all. Okay. Chain rule and all, we know that, okay, P02 by here. In the case of, okay, we can get after the sock, we can get the P02 by P2. That's going to be. And also, we know this across the sock how the even pressure is going to be there. We know all those relations. Okay. So we know that P02 by P2, we can write it as 1 plus gamma minus 1 by 2 m2 square whole to the power your gamma by gamma minus 1. And also you can write your P2 by P1 as a 1 plus 1 minus gamma. Okay, or like that we can. So these also we can substitute in terms of your Mach number. Okay, that is m2 as a function of m1. Same way, these also we can write it as a function of m1, your P2 by P1. So if you are going to resolve it, whatever this equation you are going to get here, a chain. So what will happen? This is going to be P2 cancels out. We are going to get P02 by P2. This one we are going to get it as a function of here. So already I told you to draw the TS diagram for that. I think you people have done that. Okay. Between 1 and 2, what has happened? Let us take a case of, okay, this is the one. This is your sock. Okay. Let us take this is infinity 1, 2. Okay. Further. Okay. Here let us take any one of 3. So what will happen? Your T. Yes. Okay, in the zone infinity to 1, okay, your temperature is going to be constant and your entropy also going to be constant until the point of 1. And then across the sock, what will happen? Your temperature is going to increase and your entropy also going to increase. This is 2. And then between 2 to 3, you have a entropy is constant, temperature also going to be constant. This is your TS. So these are the things they taught me during my MTech days. Okay. So they will give the question is straight away like that. They are going to give a Pitot tube. Detached stack is going to occur. Draw the TS diagram. Okay. Mark all those points. Draw the TS diagram for that. And estimate the P02. How are you going to estimate? Yeah. Any questions, sir? Any question?
Sir, no question.
Thank you. Okay. So if you have anything other than these, whatever the one, if you have any doubt, okay. So next class I'll take up the blowdown time for a supersonic tunnel. If I have time, I start up with the uncertainty estimate also. Okay. I need another one more class on Friday. If you can give me morning itself, it's better for me because I have some documentation work outside office. I have to go to register office for documenting something. I think most probably it's going to be on Friday. Yeah. Anything else, sir?